Hi everyone. We will start shortly. We just wait 2 to 3 minutes that everyone else join the webinar, and then we can start. So it's 5 minutes past 5, so we wait enough for everyone to join. Hi everyone, thanks for joining to our webinar. This webinar is about the Simpleware software, and we will learn how to use Simpleware for the patient-specific modeling that we use in our biomechanics analysis. So this webinar today will be around 45 minutes video recorded presentation by Dr. Thomas Spirka, and then a 15 minutes Q&A session with Dr. Ross Cotton. Before start the webinar, I would like to again introduce our student committee team who is responsible for the webinar series. So as you may know, the student committee is running by Dr. Aurelia Carrier, the head of ESB student committee, and myself, Ehsan Sudman, and Rodrigo Romarovsky. We are, as a member of the student committee, are organizing the webinar series. Unfortunately, Rodrigo is leaving us, and this would be his last webinar with us. He helped me a lot to establish this webinar series and also coordinating 8 successful webinars, I would say. And I would like to personally thank him in the last webinar for all the efforts he made and all the helps that I got from him. And Rodrigo will be replaced by Chiara. So Chiara is a new member of the student committee, and she would help me in the next webinar series for the organization, presentation, coordination, and everything that we need in this matter. So Chiara, do you want to introduce yourself briefly before we go forward?
Yeah, sure. I'm very happy to be here, despite this means that we have to say goodbye to Rodrigo, who did a very great job. Maybe just a couple of words about myself. My name is Chiara Datti, and I'm currently working on my PhD project at the Julius Wolf Institute in Berlin in the field of computational mechanobiology. And yeah, I'm looking forward to organizing many engaging webinars within the ESB.
Great.
Thank you.
Thanks a lot, Chiara. And as I said, this webinar is first presenting a recorded video by Dr. Thomas Spirka, Senior Application Engineer at Synopsys company. And then Dr. Ross Cotton is with us today to do the Q&A session. So just about Ross, he is the Application Engineer Manager now in the company since 13 years ago. And he received his PhD in sport engineering from Loughborough University, and his research or his PhD thesis was combined experimental test and numerical simulation to investigate the surface interaction of a soccer ball impact with the support of Adidas company. And he is now in the Synopsys company as an application engineer manager, where he oversees the software technical support and consultancy of the project. So I would now run the video. So we will encourage you to write down your question in the question box down in the tab of the software. We write everything down, and after the video, we can discuss all the questions that you have. Enjoy the video.
Hello, and thank you for joining today's webinar, where we'll be focusing on taking a look at the Simpleware software solutions for creating image-based modeling in orthopedic applications. So what we're going to primarily focus on in this webinar is taking a look how the Simpleware software can be used to basically take in image data and create 3D computational models of that. And we're going to focus on how this technology and these techniques can be used with regards to orthopedic applications. My name is Thomas Sparka, and I'm an application engineer for the Simpleware software. I've been with the company now for 7 years, and the way I've structured this webinar is as follows. We'll start by giving you an overview of the Simpleware software, just kind of give you a review of what the software is, what it does, and some of the features that it has. And then I'm going to move on and focus mainly on the software demonstration, where I'll be opening the software to show you kind of like a workthrough for a workflow for creating an image-based model of the pelvis. So let's launch into this. So start out with the Simpleware product group is part of the larger Synopsys Corporation. And just to give you an idea on the Simpleware product group, it is a focus group where we focus exclusively on developing the Simpleware software, which is a high-end 3D image processing software. To that end, we have dedicated sales, support, and service teams in this area, and we have a global presence. And this software has found applications in many different fields, including clinical, life sciences, materials manufacturing, reverse engineering, and many more. And it's found applications in both the commercial and academic spheres as well. So to give you a more in-depth introduction to the software, what it is exactly the Simpleware software. The Simpleware software is software that is primarily designed to work with patient-specific data, meaning that we want to take in patient-specific image data and construct models from that data. And to that end, we have focused on developing the software to do with and provide the tools to do that. And the software includes a large number of tools that allows you to work with the software in a large number of different image types, as far as image data sets of varying quality and from different modalities. Meaning that we give you tools that you can use for automated processing all the way down to manual processing, depending what's needed. The software then allows you to take those models that you create and take them to a step further by allowing you to create in silico models for both analysis and simulation, meaning that you can take these models, create FEMA meshes or STLs, export them to commercial software packages for doing things like finite element analysis or computational fluid dynamics, depending. We also give you the tools that will allow you to incorporate and bring in your devices, so that you can incorporate your CAD-based devices for like knee implants, hip implants, things like that, and bring them into the software and incorporate them into your image-based model, so that you can create one model that you can then mesh and take over and do simulations on, or in some cases, do measurements, 3D print, whatever your part thing. One of the main things, though, that we are focusing on is to try and give you tools that will help you speed up your image-based modeling workflow. So one of the main things is when working with the software, there's certain things that you want to kind of look for, especially in an image-based modeling software such as these. And some of these things are what we focus on at Simpleware. We focused on creating a software that is both easy to learn and use, and we have worked with the software to make sure that it is fast and accurate as well as powerful and reliable. We also understand that as hard as we try, we can't cover every situation. So you also want to we also focus on making the software customizable through the scripting API that will allow you to basically customize the software to your particular need. While it's not as big of an issue for academic customers, one of the things that we focus and the tools are focused on is to reduce time to market for your medical devices. And to that end, we also fully support the software through our application engineering team, and the support is the equivalent for both commercial and academic customers as well. So to give you basically an introduction to the software itself, the software is GUI based, which provides a large variety of tools for various aspects of the image-based modeling process. So be it visualizing your data and including creating animations such as for presentations, we offer the tools for that. The main point of the software, and we do offer a wide range of tools of that to handle a lot of different scenarios when it comes to image-based processing and creating your models, is the number of tools we offer to do filtering and segmentation of your images. Then once again, once you create your model, the main thing is you want to do something beyond the model besides look at it. So we want to give you tools to do things like measurement, quantification, and statistics on the model. And these can range from very simple, like point-to-point measurements, up to surface area, volume statistics, and various other measurements that you can take in the software. We also give you, as mentioned, the ability to incorporate CAD and CAD geometries into your image-based models so that you can create a complete model of both your image-based model from your basically from your medical images, model from your medical images, as well as taking your CAD, incorporate those in there and bring in a single model. And lastly, we do offer the tools to take you to things like 3D printing, exporting models to CAD or FEA or CFD support, as well as do scripting and automation with your to customize the software to your particular needs. So just kind of working you through the workflow as far as what it takes to build an image-based model. So starting at this beginning, the first thing is you need to import the images. And with the software, we give you the ability to import images in a variety of different formats, including DICOM images, which is the most common for medical imaging, so for CTs or MRI. One of the things that you have to be aware of, though, when working with DICOM images is you need to make sure that you anonymize the data. And we do, and the software offers the tools to automatically automate the image data set so your project files don't contain patient-specific or confidential patient data. So you don't have to, which is important when storing the data and what security protocols you would have to use when storing the image data, because these don't have any patient-specific patient-specific data stored in the project files. You can save these pretty much like normal files. The next step is once you bring the images in, that's only half the battle. The next step is your segmentation and processing. And this is where you identify the voxels in the image that correspond to various structures. And there are a large variety of tools. The software provides a large variety of tools to allow you to do this, ranging from the automated to the semi-automated to the manual. The workflow typically needed to do your segmentation largely depends on the image data set you're working with. And the workflow depends on a number of things, such as the quality of the images, what you're trying to get out of them, whether or not there's artifacts, being metal or motion artifacts, and things like that. So we offer you a large number of tools because a lot of times the workflow you're going to use is going to vary from one data set to another data set, unless your imaging protocols are very standardized. And then it'll be very similar, but usually there's still a little bit of variation in there as well. With regards to once you get your model out, then one of the main things is what do you do with this? And there's a lot of tools that we offer that will allow you to work with your model once it is segmented, including doing things like doing measurements and doing analysis of your model, be it statistics, taking measurements, fitting shapes, kind of basically interrogating your model so you can quantify the model that you created get the measurements you would need for your particular application. Incorporating CAD geometry is often very important, especially for orthopedic applications, where you would have your device and you would want to incorporate it into your image-based model. Typically, your image-based model would contain your anatomical information, and you may want to incorporate your CAD-based design for your device. So you want to bring that device in and use it to create a single model that incorporates both, and we do offer the ability to do that. And what's more, we do allow you to basically combine the CAD and image based in the same model and do things like mesh model. So you can mesh the CAD and the image geometry in one model and export it as a single model to an FEA or CFD solver. Which leads us nicely into the next part, which is that we do offer a wide variety of options when you do create your model for putting in a format that is exportable that is most useful to you. So we can export to most of the major commercial FE and CFD packages in an appropriate format, those being like ANSYS, Abacus, COMSOL, etc. And we also offer the creation of high quality STLs that would allow you to go to 3D printing, as well as providing tools that could potentially be used to export your geometry as an IGES or a step file, should it be needed as well. Well, so here you see just another example of the model generation. If you want to go to 3D printing, there are the tools there, because this is kind of like a specialty subset of what you would do with the model. And there are certain tools that you're going to need when going to 3D printing. So you can, we do have the tools to basically allow you to create things like connectors, basically to format your model and to put your model in a format that it would be able to be successfully 3D printed. And lastly, we do offer, and as I mentioned, we can't necessarily consider every possible scenario when creating the software. So one of the things that we do is we give you the ability to do a lot of scripting in the software, whether it be through the API, where you actually write your code yourself. You can also do things like recording macros. So if you have like a number of data sets, you're doing the same process over it, just record a macro, put it basically, and then you have your script, just modify it, and then you can go each time we get to the point where you're doing the repetitive stuff, just run the script. Saves you a lot of time. And you also give you the ability to convert from logs. So when you're doing things, everything every mouse click is recorded in a log. You can go back, highlight that in, and convert it to a script. All of these things are designed to let you customize the software in ways that best fit your particular application to save you time and to automate more, make your workflow more automated by allowing you to do things like build plugins, as well as basically build plugins for your particular application, with the goal being to give you the ability to create a fully customized solution for your particular workflow. With that, I'm going to kind of summarize up just basically this part of the presentation. Basically, that's because I was just basically the point of this part of the presentation was to present the Simpleware software, what it is, what it can do, and some of the features that are available. And just to kind of sum up, it does give you the ability to create these image-based models using robust proprietary algorithms, best-in-class segmentation tools. We have designed the software so that it is easy to use as well as very customizable. We also offer very attentive and very responsive support. So this is provided through our application engineer teams, and we offer one-to-one sessions, web meetings. We can kind of tailor the support to your particular need. And we also provide regulatory certifications for the software as needed. So the last thing is to wrap this up, is to let you try the software itself. So we do offer trials of the software. There's a 30-day trial. You could also arrange personal software demonstration arrange your software demonstrations. You can also look at videos, webcasts, and download sheets from our website. And the following entries are the means of by contacting us. You can either contact us by email or through the website. So thank you. That's where I'm going to wrap up this presentation. And now I'm going to switch to what's probably going to be more of interest to many of you, and that is actually showing you how we would use the software to create image-based models. So I'm going to escape out of here and close this, and we're going to switch over to the software. So pretty much the workflow, as I kind of alluded to in that presentation, is you start with the images, you do your segmentation and create your models, and then you go from there. So what's the first step is we're going to have to import images. And you can see here we can import images in a wide variety of formats. In this case, I'm going to work with DICOM images. So I'm going to basically, I've already navigated to the folder that I need to be in. So I'm just going to select the folder that has the DICOM. The software is automatically going to detect the DICOMs, and it's automatically going to be able to read the DICOM heading, and will provide the appropriate and display appropriate information there. It is pre-programmed to anonymize the DICOM tags and remove the file names from the log, meaning that when you save your project files, there's going to be no confidential patient information retained in the files unless you alter this and tell it to basically store all the DICOM data. So in this case, we're going to just go with it as is, and we're going to let it be anonymized. So we're going to click finish, let it bring it in. And so you can see here, this is CT data of the pelvis, and it was acquired in the axial, and the software automatically can go in and convert and create the coronal and sagittal views of the image data as well. The software also can create, in this case, a volumetric rendering of the software. And what this is basically is it's a display of all the pixels, but it's been now fine-tuned to display only pixels of the higher contrast pixels in this case, which correspond to bone. One of the nice things about the volume rendering is that it allows you to get a feel for what's in your images even before you start doing anything. So a lot of times, the way I use this volume rendering is that I'll take a look at it, kind of once I load my images, get a feel for what's there, see if there's anything that I should be aware of, such as there's large amount of artifact, if I'm dealing with an implant in there, maybe there's motion artifact. This can tell you a lot about the image data set you're dealing with prior to you actually getting in and segmenting. So we can tell you really quick, say if you ask for images and you didn't want implants in them, you see an implant here, well, no point in going any further, go out and go back in. Or if you specified images with implants, got one set of images that doesn't have the implants or not the right one, you can kind of get an idea from that and go from there. So now that the software has been imported, the next step is we have to start working on building our model. As mentioned, the volume rendering, while it looks nice, doesn't necessarily contain the data that you would need to create your model. So basically, it doesn't identify those voxels that correspond to different objects. It just displays all the voxels. So the next step here is I'm going to start working on the segmentation. And one of the first things I'm going to do here is I'm going to resample the image data to make my voxels cubic. So basically each one of these pixels has now, when I imported it, it extruded each slice by the slice thickness as determined from the DICOM header to create a voxel. So that's going to give you your volume, your pixels, their volume, and will allow you to create a 3D object. Now, I want to make those voxels cubic just because there's certain tools such as the smoothing filters or some of the other filters that work best when you're dealing with cubic voxels. So I'm going to basically make all the voxels 0.78125 in each direction. So we'll start by doing that. And then we're going to move on to the next step, which is identifying those voxels that correspond to the bone in the geometry. So we want to get essentially all the bones right now. We'll worry about splitting them up into individual structures in the next step. So what I'm going to do here is, because I have very good contrast between the bones and the surrounding tissue, I should be able to get away with using a threshold. And the threshold tool, for those, if you're not quite familiar with the software, it's simply a tool that allows you to specify a range of grayscale values, and will take all those grayscale all the voxels that have grayscales within that range, and we'll assign them to a single mask in this case. I'm not 100% sure whether or not my data is all as one, or basically, or if like I would lose, basically if I only kept the largest island, if I would maybe lose the femurs or something like that. So I'm not going to, so I'm going to want to keep all the islands, and I'll go about cleaning this up once I do my initial segmentation and see what I get. Right now, just looking at this, it looks like I should retain everything, but we'll go with it as this way, and I can use other tools to clean it up. So I'll click apply, and you'll see that a new mask has been created. And when I refresh the 3D view, you'll get a feel for basically what was captured by the threshold. So you see we got all the major bones that we're interested in, but we also picked up a lot of other noise and other small structures that had grayscale values that were within that threshold range. So I want to get rid of these. And the way I'm going to do that is I'm going to be using basically what we call a mass flood fill tool. What the mass flood fill tool it does is it allows you to basically pick an island. In this case, I'm going to pick the island that corresponds to the pelvis. And what it'll do is it'll actually retain that island while getting rid of any disconnected islands that are not attached to the island I picked that I picked. So if I zoom in here, click on the pelvis and refresh, you'll see that all the small non-connected islands have disappeared. So I now have a pelvis, and it depends on my next step here is kind of depending what I need to get out of it. If I just need to work with like the pelvis and I want to just create a single model with all the structures in here, maybe just for 3D printing purposes, I don't have to be very precise. I don't have to pick one out. Well, then I could just work with this mask, clean it up, and create something that would be suitable for export to 3D printing. It would just show up as one object, but you would be able to see the femurs, basically more like like creating an anatomical model of this. But in this case, I want to go a step further. So I want to basically split this apart. So I want the femurs to be separate objects. I want the ilia to be separate objects, and I want the sacrum to be a separate object. So to do this, I'm going to use a tool we call split regions. And what the split region tool is, it allows me to create basically markers or denote structures by creating a submask, or basically a markers mask, as we call it, to denote each structure. And then what the software does is it will use the grayscale values and take a look at how I generate those markers masks and try and split and we'll try and work on splitting the island that I'm applying this to into those different properties. So what I'm going to do is I need to start by creating those markers, and we have created presets for a lot of the cases you're going to see in orthopedics, such as ankle, cervical spine. If you're working in cardiac, we do have the one for the heart, the hip, the knee, the lumbar spine, maxillofacial, shoulder, or thoracic spine. In this case, we're obviously working with hips, so I'm going to do that. And all this does is it creates placeholder masks and basically asking me for which objects I want to segment out of it. So what I'm going to do now is I'm going to specify hip left, hip right, the sacrum, and femur left and femur right. So in this case, I want to zoom to a slice where I can really see what I'm doing here. So I'm going to go to this slice right here because I can really see the ilia of the pelvis. I can see both femoral heads very well. They're very well defined. So I can create a very nice markers mask that will allow you to break this apart. Now, when specifying the markers mask, you don't have to be too precise, but better information, as the old adage goes, the better your information you put in, the better your results will be. So I'm going to start with hip left, and the one thing to remember, this patient is supine, so hip is going to be on the right-hand side, the left side is going to be on the right-hand side of the screen. So I'm just going to kind of follow this contour of the ilia here. For the left, and I'm going to do the same thing really for the right. And we'll go down in here and create something like that. And then I'm going to skip the sacrum for right now. And I'm going to select the femur left. And once again, I'm going to kind of follow the contour of the femoral head here, just to make sure I get, just to give the software kind of an idea of what it's supposed to look like. And I'm going to do something similar for the right. Now, the image I chose here is good for these four objects here. Now, I want to do want to get the sacrum. So I'm going to shift to another object, another slice. So I'm going to kind of scroll through here until I see the sacrum coming in. And this is starting to look good. So, but I'll move it on a little bit more. And right about here, because I can really see where the pelvic, the ilia and the sacrum come together. So now I'm going to go with the sacrum here, and I'm just going to draw a marker's mask for this one. And on the left-hand side as well. Now I'm basically going to allow the computer to take a look at it. It's going to take a look at the markers masks of the grayscale voxels that I selected for these various objects, and it's going to try and use the grayscale values underlying those basically denoted by those markers masks, and we'll try and utilize that to basically back out the different structures. But this is one of those cases where I'm going to try and use the computer horsepower rather than my own personal horsepower, meaning that I'm going to let the computer do the work. I could segment this all by hand, but it's going to be much faster to do it this way. And it's going to take a minute to kind of work through this, but I assure you it would be much faster than would be if I actually did it by hand. So I'm not going to keep the markers mask right now. And we can take a look and see what we've got from the segmentation. And you can see it's done a very good job of splitting these apart automatically. Now, the one thing here is the semi-automated, typically for these particular workflows, is automated and semi-automated tools can get you a good part of the way to creating your models. But typically all the segmentations and all the workflows ultimately require some manual cleanup to get your objects into a format that you can use for modeling. So I'm going to give you basically, I'm not going to do all of these here just because in the interest of time, but I'm going to show you the basic process for cleaning up some of these data sets. And I want you to keep in mind that regarding time, how long it's going to take me to actually do that. So on just one, and basically because we have 1, 2, 3, 4, 5 objects here, so you pretty much have to multiply it by 5, maybe more so because the sacrum, due to the complexity of the sacrum. But I'm going to work out with the left femur, so I'm going to isolate it. And let's take a look at the left femur and see what we have here. So it's not looking too bad, but you see here that we the threshold that original threshold didn't quite get all of it. So we kind of have to fill this in here. There appears to be a little bit of a hole up here, and it's kind of still looking kind of rough. So what I'm going to do here is I'm going to start working on closing this off and basically cleaning up the model to put it into a format that would be suitable for modeling. So the first step is I need to close this off. So I'm going to use the paint tool, but I'm not going to paint on every slice. So I'm going to basically find the left femur, and we're going to start right about here. So I'm basically, you can start seeing here where the original threshold, what the parts that were missed. And I'm basically going to use the paint tool to try and fill those in on this slice. So I'm going to just basically use the paint tool, follow the grayscale values to kind of fill in those areas that were missed. But I'm not going to do every slice. I'm just going to do every fifth in this case. And this is one of those things that when doing these segmentations, you start, as you do more and more of them, you start to develop a feel for what needs to be done and how you should apply the tools. Just in this case, like how many slices you're comfortable with skipping here and letting the next step fill in for you. So it is a little bit of it does require some experience when you're working with this to learn how to use the software and how best to use the tools and apply them to a given situation. And I think we need to go just one more for right now, and we'll see what this gets us. A lot of this is, especially when you're doing your first segmentations, it's a little bit, it's going to take longer, and because you're not familiar with it, and as you build up the skills with the segmentation, things get faster and faster. So once I did those 5, so let's take a look at what that filled in. So you can kind of see how these are going to fill in. So I created every 5th one. So now I have something that looks like this. Now what I can use is I can use a morphological close tool. And because I skipped 5, I'm going to set the structuring element to 5 pixels. So it's going to basically dilate out 5 pixels and then erode back. The thing here is, as it fills in those gaps, as it erodes back, the filling will remain intact. So what you're going to see here is after I apply this, and we'll refresh the 3D view. You can see how it closed in those regions. Now I do have this one region here that's still a little problematic that I would want to clean up. So I'm going to go and apply to that surface here using a keyboard shortcut. And I'm basically going to, once again, use this, and this is going to be a very manual process here. So I'm going to use paint because I'm getting right to the boundary of the object. So I'm just going to kind of go in here and clean, basically assign. And maybe one more. To basically fill in this part that was missed. So you can see right there. Now this is looking pretty good, but there still may be some small cavities or things of that nature within the femur itself that I don't necessarily want. So I'm going to run a cavity fill tool, and what this is going to do is going to basically look at any openings in the mask, and if it's completely surrounded by voxels that belong to the femur, it'll basically close those in. So it basically closed in and filled in any holes there. So now this is almost ready to go, but you can still see there's some stair stepping due to the fact that these are based on voxels and that it was created from slice data. So to handle that, I want to take it one step further, and I'm going to run the recursive Gaussian filter. And I'm going to binarize it before smoothing, which means that it'll basically take the mask and it'll assign it all one basically value, and everything else will be like zeros. So it basically creates like a binary images before smoothing. This helps with the smoothing process because you don't get partial volume effects in that. The other thing to pay attention to is your Gaussian sigma. I'm going to set it at about 1.3 pixels. The higher the value you set it here, the stronger the smoothing. So it is possible. The one thing to keep in mind is the more you smooth an object, the more you defeature it. So you start losing little features and little things on it. Now, sometimes that's necessary depending on what your end goal is. But for this case, it's a decent smooth, but it's not over, but it won't be over smooth. So if I click apply, kind of see it got rid of the stair stepping while still maintaining the nice shape of the femoral head here, as well as the marrow channel at the bottom. So you can kind of see that this is the process, and it's for this. And then the next step would be is I'd probably go with the right femur, clean it up in the same manner, clean up the two left and right, basically the hips or the iliacs, and then the sacrum itself. So you can kind of get a feel for that. And I would estimate that if I did this all, basically worked on it, as I would do if I was creating it in this method, say I just had a one-off of these, I would say it would probably take me an hour to clean it up totally and get this model ready for the next steps. Now, that's not too bad if I only have like a handful of these, maybe 5, 10, it's probably not worth it automating the process at that time. However, if I'm doing, say, 5 to 10 a day or even 5 to 10 a week, for, say, I'm doing like work for an in silico trial, or we're doing like a large number of patients for a specific study, then we may want to look into more of the segmentation tools. And to that end, we have developed automatic segmentation tools for several common anatomies, being the ankle, the knee, both CT and MRI, as well as hip CT. There's also one for cardiovascular applications that can automatically segment out the heart. Now, these algorithms are based on artificial intelligence and machine learning. So this means that they've been trained on a certain data set to allow it to do the auto segmentation. And for most like adult CTs, they will probably give you pretty decent results as long as you don't have things like implants in there and things like that. Now, it can potentially handle the implants, but they weren't trained with implants, so it's something B. I would definitely try it with the implants, see what you get, because in a lot of cases we've gotten really good results even when there are implants in there. But it's ultimately something that you're going to have to pay attention to. The other thing is that you want to basically, when using the auto segmenters, is that you have to make sure that what you got out of it. So this isn't a blind process. There does have to be a certain amount of quality control to it. But the one nice thing with this is I'm going to just close this and open it again, just to show you the process for using the auto segmenters. So if we basically import those DICOM images. Again, all I would really need to do here is open the auto segmentation, click on the hip, and click apply. I won't do this now. It does basically do the segmentation in about 3 minutes in this case. However, it's basically 3 minutes of dead space during a webinar where we just basically walk progress bars go across the screen. So what I'm going to do is basically show you the output of this. So if I hit apply, wait about 3 minutes, you would come back and you would get something like this, where everything's automatically segmented out into a format like this. So it is a much quicker way to do things, and you can use this for batch processing. Now, the one thing to pay attention to as well with the auto segmentation tools is a lot of times, like even when the case of implants, it'll get you something. And it'll usually get you, a good ways down the road to creating your model. However, it won't necessarily get you 100% all the time. I guess that would be the best way to put it. So typically you would get this out. It would be a large time saver because now you don't have to go through and work with this. In this case, you may have to do a little bit of cleanup on certain aspects of the model. If we look in close, you can kind of see here, there's a little bit of a connection here that we would probably have to clean up. Maybe you have to deal with this over here and a couple of other things, depending on what you need. Maybe clean this up, depending on how you want your model to be. But this will get you further down the road, but you will ultimately have to do some checking up on it. And you will also, especially if you're doing batch processing, you're going to have to do some quality control, make sure you got out what you think you got out of the auto segmenter. So the next step then is to go and so pretty much now that I have my model, the next step is now we can try and play around with it and see where we want to go with it. So one of the first things a lot of times that people want to do with these types of models is just do things like measurements. So we can do things like just point-to-point measurements, say right here. Basically what you're seeing here are all the landmarks that were generated as part of the auto segmentation. And you can basically, we have designed the auto segmenter to identify the common landmarks for this. Should you need to create your own landmarks, you can generate them by just creating a point. And it'll create another landmark. You can call it whatever you need to. So you can create that point, you can create new ones as you need for your particular model. You can take things like just point-to-point measurements. As well as doing things like checking angles. As needed. So you can do quite a bit with the measurements as well. You can also, in some cases, it's important you would want to take a look and maybe fit like spheres to the femoral heads or maybe the acetabulum. So that is also possible with the software, and you can use those spheres that you create and do shape-to-shape measurements as well as creating basically getting a fully understanding all the dimensions of those particular shapes so that you can quantify the object. So just to I'm going to show you really quick how that can be done. I'm going to isolate this femur. And toggle off that angle because we don't need it right now. And I'm going to go to shape fitting. And I'm going to basically tell it a region of interest. And I'm going to use a primitive in the form of an ellipsoid to identify basically the region of the femoral head. And I can identify this and figure out just exactly what region I would want to fit this to. I would then use a sphere. And then if I click fit, it will basically fit a sphere to that. So let me just delete this, and we would see we basically fit a sphere to the femoral head. I can then look at that sphere and get a feel for basically the parameters of that sphere, such as the radius, the center, the diameter, the area, the volume. So this could be a stand-in for the femoral head should be needed. And you can do this with a large variety of other objects in here too. You can create another sphere for the other femoral head and then use shape-to-shape fitting to basically measure the distance between them. So that's one option here. But ultimately what you want to do here in a lot of cases is you want to go beyond just creating a model in the image-based space, and you want to take it to other software packages for further simulation as needed. So one of the things that I'm going to demonstrate now is I'm going to show you for the models how to basically, we can go to a model. So we can, in this case, I may want to go take this to FE. So I can select this, pull it into the model, and then I can then set up the model to create an FE mesh of this. And we can export into a large number of different formats for most of the commercial software FE analysis packages out there. I can also change the model type to surface, should I need to go to 3D printing, or create potentially NURBS if I want to go to a CAD geometry as well. But for this case, I'm just going to use FE just to give you an idea of what can be done as far as creating these models. And you can make these models as complex or as simplified as possible with regards to mesh. You can set different meshing parameters for each object in the model you have. And you also have full control over the meshing as well. So you can specify the element size and how quickly it grows. Basically, you have full control over the meshing. The one thing to note, though, if you are creating meshes, you will be creating what are known as orphan meshes. So you will need to do things like create contacts in the software. So you can create contact surfaces to identify objects that are in contact with one another, as well as create what we call node sets. And these would be creating these node sets would allow you to specify the nodes within like a given region that could then be used for setting loads or boundary conditions for that. So if I were to set this up and actually run it, so the next step would be to run the full model. Once again, in the interest of time, I'll just pull up the completed object. So and this will take a few minutes, but you can see here that it is possible to generate a mesh out of this and then export it as needed to the appropriate folder in the appropriate format. In this case, if we're going to Abacus, it would export it as a .imp file and allow you to export it to Abacus. Pretty much that's kind of everything I wanted to show. We do also have the ability to import STLs and place those as needed. But however, that will have to be the subject for another time because we are running out of time for this webinar. So I'm going to wrap things up there. We will now take it into question and answer period. So I'll be happy to answer your questions as they've been posed. So I thank you for your time and I thank you for watching this webinar. And if you have any questions, please feel free to contact us as well. Thank you.
So I hope you enjoyed the video. So now we would like to go through the questions that were asked during the session. So Chiara, note down all the questions. And Chiara, maybe you can start with your questions and Ross would answer all the questions.
Yeah, the first question asked by the audience is there any way to interact with the software through scripting such as Python so as to repeat a certain process or perform local operations?
Okay, I mean, firstly, just say Tom's sorry he couldn't attend today. He's off on an unexpected travel with work, so I'm just taking his place. But in terms of scripting, I think Tom mentioned about the macro recording, the scripting capability, the scripting API. So that's going to be using Python and C#. So what we kind of say about the software is anything you can kind of click, you can script. So if it's something you can manually step through and replicate, and it's something which can be automatable. You can build in inspection steps as well. That's quite useful. But yeah, you can kind of automate what you need to, as long as you can repeat it and you can do it manually within the software. Then it's a really good candidate for scripting.
Okay, thank you very much. So the second question that I have is there any possibility to assign material properties based on the gray values? So I think to assign effective material properties from medical images.
Yeah, we do have that option. So once you've generated a finite element mesh like Tom showed in the last step there's a materials tab in the software that allows you to either set a placeholder, so you can edit it later in Abacus, Ansys, or Console, whichever package you're using, so you can use any of their material models. You can set up a simple linear elastic model, or you can use like the grayscale based materials. So you can vary the materials based on the underlying grayscales or Hansfield units, typically for CT. And we do provide some defaults based on the literature, but usually you would probably take some values from the literature papers for your anatomy, maybe in the various loading directions. And then what you do first is go from handful units to density, use your linear mapping, and then from density to Young's modulus stiffness. So you can do that kind of two-step process, and there's a variety of options in the software to use different mappings, save them, share them with colleagues, and also manually edit them as well, and change the number of steps and so on. So there's a fair bit of functionality for mapping grayscale values to material properties.
Thank you very much. Another question regards mesh refining. So are there any tools to refine the mesh in terms of size and number?
Yes, there's quite a few options. So using just the defaults, kind of Tom showed, that they're kind of based on topology. So the mesh will try to adapt based on topology automatically. So you can set various controls which will try and do that, and you put smaller elements around smaller features, whether it should, and kind of adjust the controls on that. We do have also local mesh refinement, so you can use a variety of shapes and objects and free-form objects to set local mesh sizes, both on the surface of the objects and also within the object. So if you put like a sphere kind of region of interest on the femoral head, you can refine the surface, but also the internal elements, so you don't get a kind of sudden jump from small elements to big elements inside that kind of zone as well. So again, there's quite a few number of options and settings to do that.
Thank you very much.
Great.
I cannot see further questions.
So please write down your question in the question box. If you don't know where you find it, it's underneath of the tab of the software. Since audience thinking about the questions, I would also ask you, is there any Boolean operation option in the software that we can remove a part of the bone or something like that?
Yeah, so we kind of work on two levels in the software. We can work on voxels, so do booleans on voxels, so a mask minus a mask, or a mask plus a mask, or an intersection between two masks. The other one, we also work with surface objects. So if you import an STL, we can also do booleans on triangles very robustly. So for example, if we bring in an implant, and that's obviously a surface-based object, tessellated, when we get the bone to a tessellation, we can do an implant overlap with a bone, for example. So you can do a robust Boolean that way, and then generate your finite element mesh in that process. So whether it's a voxel-based object or tessellated objects, we've got those options for various Booleans.
Yeah, thank you. Chiara, is there any question left from the audience?
Not really, but actually I might have a question.
Yes.
So for example, in the video you show that when you have to split the regions, for example, hip, left, right, etc., so you draw some markers, but are there any protocols to draw these markers, or is just by experience that you do that in that way?
Yeah, I guess it works better when you're working nearer the joints. So as Tom showed in the video, that if you kind of draw a rough guide around the joint space on either side, obviously, that tends to provide the best results. What Tom maybe didn't show is also you can do it in 3D as well. So if you have a 3D rendering, you can paint on the 3D model and create the markers that way. So sometimes people prefer to work in 2D, sometimes in 3D. But generally, you kind of, over time, you kind of work out what's needed, and you kind of can do as little as needed to provide the split. I guess in very arthritic cases, you might want to, or compact kind of joint spaces, you might want to provide more guidance to the splitting. But if it's like a primary case, kind of healthy person, then maybe you don't need too much guidance for the tool.
Thanks a lot. So I think
Thank you.
the time is almost finished. So we are also 2 minutes over. But thanks a lot, Russ, for your time to answer all the questions.
Sure.
And thanks a lot also to your company that you provide this opportunity to present the ability of this software that everyone can use. So this webinar will be saved and uploaded into ESB YouTube channel. So you can see it again, and you can still write down your question underneath, and we can deliver your questions or forward them to the to Tom or Russ. Thanks a lot, and I would like to close the session now, and hope to see you again in our webinars. Thank you. Have a nice time.
Thank you.
Thank you.
Bye bye.